Okay, welcome to Lesson 2 in Chapter 5 on Triangle Bisectors. We have a lot of new vocabulary, so let's get to it. I'm going to go a bit out of order, so let me explain the words, and then you can pause the video to write them down. Let's start with concurrent. Concurrent is intersection of two or more lines. That takes us to point of concurrency. Point of concurrency is the intersection point with triangle line segments. Then we have two kinds of points of concurrency. The first one is circumcenter. Circumcenter is the intersection point of the three perpendicular bisectors, and then incenter is the intersection point of the three angle bisectors. Then we have circumscribed and inscribed. Circumscribed is when a triangle is contained inside a circle and its vertices intersect the circle. Inscribed is when a circle intersects each side of a triangle and has no points outside the triangle. So let's take a look at a picture. The first one is a circumscribed circle. That means that the circle is outside the triangle. Each of the vertices of the triangle is on the circle. Then we have an inscribed circle. An inscribed circle is inside the triangle, and its radius touches the sides of the triangle, but no part of the circle is outside of the triangle. We'll be working on those a little bit later. Okay, Theorem 5.5 describes the circumcenter, which is where the three perpendicular bisectors intersect. It says, the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. Okay, we are going to do some constructions in class later this week, but let me show you how we find the circumcenter, and you can kind of look at how the relationship between the circumcenter and the perpendicular bisectors work. Okay, so here we have a triangle, and if we want to find the perpendicular bisectors, first one's easy because it's going to be perpendicular and through the midpoint. So this one we can look at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So right here's the midpoint, and the line perpendicular to that base is going to go right through here. So here we have a perpendicular bisector, and these two parts of the side are going to be congruent. Okay, we can do the same thing with the other one. If we want to figure out where the middle is, we can use constructions, and we're going to a little bit later, but it looks like the middle is going to be right here if we measure it. And then I'm going to use my compass, protractor. I always mix those up. Protractor. Okay, and I'm going to line it up so if you see this line that goes across the middle here, so that it kind of blends with that side. Okay, so that means that it is perpendicular to the side of the triangle, and I can go ahead and draw that triangle line segment. And then finally the last one, if we measure this, it looks like it's going to be right about there. And when we line up our perpendicular lines across the side, and you can tell that this is pretty close to perfect because it lined up exactly in one spot. That's going to be our circumcenter. So circumcenter is going to be right there at that point. So those are our three perpendicular bisectors. Okay, so we could use constructions to go ahead and figure those out, but here's what we want to do. Our circumcenter is going to be right there. Okay, so really all we want is the line that goes up to it. So let's go ahead, we'll mark the circumcenter, and then we're going to erase the points that come after that. Okay, so we've got these two right here. All right, now we have a special relationship between the circumcenter and the rest of the triangle. It turns out that if we draw lines to connect the circumcenter to the vertices, we will have congruent line segments. So it looks kind of like this. So it goes from there, and then from the circumcenter to this vertex, and then finally from the circumcenter to this vertex. And each of those lines is going to be congruent. And so it looks like this. So these are our perpendicular bisectors. And then we could have done another one, but you only need two in order to see where they are going to intersect. And that's going to give you your point of concurrency. And then from the point of concurrency to the vertex, we have line segments that are congruent. And we will use those a little bit later. Now, if we wanted to draw a triangle inside a circle, so a circle circumscribed around a triangle, we would open up our compass so that it is the same distance as that line segment that we just drew from the circumcenter. And then we can draw our circle, and it's going to go a little off kilter because I've run out of room, but I'll go ahead and finish it up this way. You can kind of see where that circle would be. The circumcenter is the center of the circle. These line segments are going to be your radius, so that's what you open your compass up to. And you get an inscribed circle, or circumscribed circle, which comes from the circumcenter. Okay, now let's go ahead, turn this over. We are going to work with this in class. We're going to do some work on the Chromebook. So as soon as you come in class, we'll probably get those opened up. Make sure that they are charged when you come to class. Okay, other side. Let's take a look at the incenter. So theorem 5-6 discusses the incenter. The incenter is the point of concurrency from the angle bisectors. And if we look at angle bisectors and the incenter, there are some interesting relationships with those also. So here's my triangle. If I want to figure out where my angle bisectors are, we did these constructions a while back, like beginning of school. Okay, so I would cross that. Both of those lines from the vertex. Then I'm going to close this down, and I'm going to make a mark right there. And then from the other side of the triangle, I'm going to make a mark right there. Okay, that is going to give me a point of intersection that I can use to draw an angle bisector. So if I have bisected those angles, and that means that this angle and this angle are going to be the same size. So we can do that with any of these. And just to show you what it looks like when it's completely done, okay, we have all three of our angle bisectors on here. Each one of those, I made an arc across the two sides and then used those two intersection points in order to make another point and drew my line. And I did that from each one of these, and then, so it wasn't quite so messy, then I erased it. Now, there's an interesting part of this also. This right here is going to be our incenter. Okay, that's where that point of concurrency is. If we erase everything after the incenter, then it's going to kind of look like this. Okay, so this part is erased, this part is erased, and this part is erased. Now, this is interesting because the shortest distance to the side from the incenter, keeping in mind this is the incenter, the shortest distance to the side is going to be perpendicular. So a perpendicular line from, and I'm going to do this the same way I did before. I'm going to line up the side of the triangle with that, and it's easy to do with this one because it's going to be parallel to these lines on my graph. Okay, so I have this right here. Then I'm going to turn this around. I'm going to line it up like I did before. So I'm going to start at my incenter, and then I'm going to line up that line so that it goes across the side, and that gives me a perpendicular line to the side of the triangle. And then one more time I'm going to do that. So I'm going to line up here at the incenter, and then I'm going to line up that line until it completely disappears. And then I have my three triangle line segments, and each one of these is also going to be congruent. So, not the actual angle bisectors, but the distance to the side from the incenter that we get from the angle bisectors. Also, something else that's interesting, if we want an inscribed angle, it comes from the incenter, just like a circumscribed triangle comes from the circumcenter. So I want to make sure that my compass is opened up the same distance as the lines that I just made. Okay, and then I'm going to use my incenter, and I'm going to draw a circle that touches the sides of the triangle but does not go outside the triangle. And it looks kind of like that. So, we are finished with that. Now we are going to work on some problems. So, take a look at problems 1, 2, and 3. We're going to use the relationships that we just worked with in order to figure out the missing lengths of this triangle. So, I have perpendicular bisectors. That would be this one here, and this one here, and this one here. Okay, now you can look at these and tell that they are not congruent. It's the other part that is. So this part, and this part are the parts that are going to be congruent. So when it asks for AT, AT is going to be the same as CT, and we know that CT is going to be 6. When it asks for RC, this is a perpendicular bisector, so it's cutting this side in half, and if this side is 5, then this side also has to be 5. Okay, now let's take a look at angle bisectors. So we have angle bisectors, and that's right here, and they don't even have the third one. That's okay, but you can tell that these are not congruent. You can tell by looking at them that they're not. However, the segments that are formed from the incenter to the sides are congruent, and they look congruent. And so we can use that relationship to figure out the length of PK. So if the length of PK, or the length of PJ is 5, then the length of PK is also going to be 5. Okay, perimeter of APL. Okay, so here's our triangle right here. Okay, and I know that this hypotenuse is 13, and I know the shorter leg is 5, so we're kind of looking at something like this. So 13 and 5, and this is a right triangle, which means I can use Pythag. So I can say 13 squared minus 5 squared, which is 169 minus 25, and equals 144. And I can take the square root of that, and that's going to give me a side length of 12. Now to get the perimeter, I add them all up. So 12 and 13 is 25, plus 5 is 30. Okay, last one. So let's take a look at this. Down here, we've got an inscribed circle. So our inscribed circle is going to be right in here. And if you look at the radius, looks like the radius is the same as these sides right here, from our incenter to the sides of the triangle. So that means that PR and PQ are going to be the same, or QP and RP are going to be the same. You can say that either way. So if they're going to be the same, then see if you can set up an equation that uses both of these, solve for x, and then substitute it back in to find the radius. And we'll check your answer when you get back in class. So, looks like that's it. If you have any questions, make a note of them and we will talk about that. Otherwise, I will see you later.